Steve Parman, Brown University. Bill, craters on Mercury. Have you looked, would anything hit Mercury from your swarm?
Yes, I haven't looked at it. Almost certainly they would. Putting Mercury in these dynamical models is a big pain because then you have to lower your time step, and that means a lot more computation time. It's something we could do, but what we also would need to do is someone would have to count craters superposed on the biggest craters there to see if we also get a similar alignment. It could be done. It's a great project. Maybe a proposal for someone. So.
Yeah, again, question for Bill. You mentioned at the beginning there was some kind of peculiarity about your result with Becky Ghent and this result. So can you clarify that?
Oh, so what is it? Oh yeah. Oh, okay. So what we did, I went a little fast. We had a paper led by Becky's grad student, Sarah Mazuret. And what we did is we tried to look at rock abundance on the moon, and rock abundance breaks down from over time. And we knew this from the divider data. And we tried to use that as a proxy for the ages of craters. And what we found is that the impact flux seems to go through a major change, about at least a factor of 2 change, about 300 million years ago. And then it becomes fairly shallow. And it may stay shallow for a long time. So the background impact flux, let's say 400, 500 million years or more, may be much lower than it is today. So that's what I meant by that.
But just in that data, you don't see any evidence of this spike, or it's just not sensitive to that age?
It may just be too narrow, or we may not be sensitive. The problem is that, rock abundance is not a perfect proxy for getting ages. And when we looked at it before, I was hoping we would see something, but we didn't see anything that really stuck out at us. But the crater counts are probably more diagnostic. So that's why I'm going with it. Excuse me. That's why I'm going with it.
Hey there, Bill.
All right.
Mike Lucas, Florida Space Institute. So I want to ask you about ground truth on the Earth for
Yes.
your shower event at 800 million years. And I'm thinking about the El Chondrite example,
Mhm.
the Ordovician event, where, and actually in some marine sediments, they found meteoritic material. So I don't know where on the Earth could you possibly find this? Is there any rocks, of this age where may preserve some? And then also, I'm not familiar with the Eualia family. What type of asteroid is that? And does that have a meteorite analog?
Yeah,
That's,
so-
yeah.
Okay, so a couple questions there. As for a surface expression, I've talked to people in the field that do this. I think the reason, first of all, the older you go on the Earth, the harder it is to find good outcrops. And sometimes good outcrops exist in the most obscure places, right? So I think even Andy Knoll's stuff, I think a lot of it's going into Greenland and everything else where it's tough. So I'm not the expert. I think I'd love some people to look, but I don't know I don't know what the status of that is. In terms of what the Eulalia family is, the Eulalia family actually is a possible source for asteroids like Bennu and Ryugu. Okay, and so well, we've even talked about this in previous papers. So it's a carbonaceous chondrite, and if it is indeed indeed a source for Bennu and Ryugu, it's probably something like a CI chondrite. So.
Hi, Nick Dygert, University of Tennessee. I have a question for Wenhao. It's a nice model, and I see how it solves problems in terms of thermal longevity and the sort of the timing of peak heat production in the moon. I was a little curious about, I guess, my understanding of the model. Are you invoking these high melt fractions to be evenly distributed throughout the lunar interior? Or is this in like a relatively restricted layer beneath the surface?
Basically, they are different. For the RMO, we are assuming a homogeneous moon and assuming that the melt fraction is homogeneously distributed, but actually that's not the case. Yeah, and then for the lunar mantle, what we did is to model conceptualized weakened region in the lunar mantle, and to see if it shared the deformation, what would be the energy, the tidal heating energy per volume. Yeah, would that be possible to generate the heating? Yeah,
I see. Yeah, I was just curious whether it's possible to maintain high melt fractions over those timescales.
That depends what we are talking about. For the RMO, we know that for some relative long time scale, it can maintain the melt fraction as we confined by experimental pathological results. But for the lunar mantle, it looks like that's not possible to maintain, for example, 10%. That's not possible. But as I mentioned, we might not need such high melt fraction. What we need is a unstable, weakened mechanism. If you consider the addition of volatiles, that can also work. And also, if we are going to consider different rheological model, different tidal response, it depends. It depends how we evaluate the energy that's required to erupt those volcanism. Although we returned lots of basalt from the moon, but if you compare those, it was mostly confined in the near side. And if you look at the thickness, the total volume compared to the mass of the whole moon, that should be a lot, a little bit, we don't know, but we had some rough estimate. It looks like we don't need so many regions in the lunar mantle to be partially molten, and don't need such high melt fraction. Yeah.
Okay, thank you.
Thank you.
I'm Hairo Hu from Brown University. I have a question for you. So say like regardless of like whether you're talking about the MLO or the mantle, if say like over a really long period of time, you have retained like certain relatively high like phi values, or it's not so high, say like 10%. But how could your model explain the formation of creep, which needs like very residual magma ocean globally present?
Okay, I see. Thank you for asking. That might be a tough one. So basically, for the RMO, we are talking about the RMO evolution, and what we need for the real case of the melt solid structure is that we need this. They're surrounded with each other, but we know that, for example, because of the density contrast between olivine and the melt, olivine will sink, definitely will sink. But we also know that what we observed, the feldspar will float to the surface. So it looks like, I think it is intuitive, and people have published that during the intermediate stage, when it starts to crystallize, for example, CPX and CPX with feldspar, the density contrast between the melt and the solid might not be so huge, might be tiny. So at this case, the solid can be surrounded by the melt, and it will be dominated by the convective force, and then consider our tidal heating. That might can work until like the feldspar state, but after that, I don't know, because the earth creep stage after that, right? So yeah,
just like say earth creep has to make the residual magma ocean fraction to smaller than say like 1%, but everything like from like the figure like you show like much above like 1%, and for the throughout the entire I'm not expecting an answer because I realize this could be interesting potential problem, but we can talk more.
Yeah, thank you so much.
Steve Harmon Brown again. I have a question for Brenna for speaker. Yeah, I mean, making 90+% of the moon in 2 days, it remarkable. I wonder if that is almost an answer or possible answer for how you get any kind of volatiles retained in the moon, because maybe it's so fast that even though these melt blobs are going to be degassing, 2 days is not going to be long enough for volatiles to diffuse out. So maybe your rapid time scale actually helps the volatile. I don't know if you've.
I have not thought about it, but thank you for solving a problem there. Then we've also thought about is maybe because of such rapid accretion and the moon is still molten at that point, you might have a very small, like an exosphere, a tiny atmosphere surrounding it. What implications would that have? But thank you for
you could just kind of do
solution.
The diffusion equation for the size of your blobs.
Yes, I can.
1% of volatiles would be retained in 2 days. I imagine most of them.
I imagine I could do that. Thank you.
Brian Day, NASA Survey. For Bill, in their paper about Copernicus and its cousins, Terada and all speculate that the impact shower here on Earth could have been a triggering mechanism for the cryogenian. But you seem to think that instead of being associated with something that was more of an extinction level event, this was something that timed more to a fertilization event. Can you talk a little bit about that?
Yeah. Okay. Well, okay. So the diversification event that Andy Knoll is seeing is happening around 800 million years ago, which is I believe before you're starting to see a lot of the snowball Earth events. Whether these impacts lead you into a snowball Earth event, I don't know. There's other things happening at the same time. Some people have suggested some of these events are related to the breakup of, I think, a major continent around this time. But the major continent breakup is not exactly 800 million years. It's sort of this prolonged event. And so it's not necessarily a great fit for everything, but it could be a triggering event for the cryogenian. So well, and you can only cover so much material. I think the implications of this, I'm still not sure about, but there's what I like about diversification from, let's say, asteroid materials is that at 470 million years ago, we have these fossil L chondrites that was mentioned by just a little bit ago. What's also interesting is almost exactly the same time, we have the beginning of what's called the Great Ordovician biodiversification event. And people like, who am I thinking of? Yeah, I'm drawing a blank. Certain people have made connections between that breakup event, which was the L chondrite parent body, and this diversification event. And it was by the delivery of reduced phosphorus in small particles and the rest of how they were doing it. So you can imagine doing that a lot for diversification, and then the impacts may have other effects. So the big impacts and the small things may be producing different things at different times. But this is something some astrobiologists are going to have to work out. They can work with me, but I need help to do more on this.
A question for Brenna and Raluca. And my question surrounds one of the ideas that's been discussed with respect to the near side, far side asymmetry. And one of those ideas is the notion that there might have been a second moon for a while that then sort of later impacted. And I'm wondering, based on both of your models, could a second moon at all be stable for some period of time? And if so, for how long?
Right. So as the person with the accretion model, we often find that there's a relatively large second moonlet, maybe about 20%. The mass hovers around 20% the mass of whatever the largest actual body is, and it can last for thousands of years, and it often reaches into a mean motion resonance with the largest moon. So sometimes we assume that they're going to eventually merge. That's been done in other works, but yes, that we often see that maybe in at least half the time, and it lasts for thousands of years. And then you've done work on this.
For the evection resonance, we haven't considered two moons, but if they were two moons, I would suspect that is going to inhibit evection resonance capture and maintaining that quasi-resonance, because there's an additional perturbation that's going to move you out of the resonance. So having two moons is not going to help removing more angular momentum.
Yeah. Steve, we have time? Great, we have time.
So yeah, Tab Preisel, Purdue University. My question was for Raluca. In the model, and forgive my naiveness, but the Earth and Sun kind of remain static in the model. So I was wondering, like, when the moon transitions into the evection, does that impact at all the Earth orbit? Or is that like a limitation of the model, or even the axial spin and that sort of stuff?
We assume that the Earth, it's kind of a semi-analytical model, what we do. So the Earth and the Sun maintain our constant, but we can calculate how much of that change would be in the semi-major axis, and it's less than 10 to the minus 6 AU. So,
yeah. Thank you.